Okay, let's just dive right into this. Welcome to our latest explainer. Today, we're taking a guided tour through an absolute marvel of modern engineering. We are looking closely at a profoundly dense, ultra-compact wastewater treatment plant. Usually when we think of industrial water treatment, we picture these massive, sprawling facilities way out on the edge of town, right? Well, prepare to have your perspective entirely shifted. We're going to see how an incredible 10-stage purification process has been engineered to fit into an impossibly small footprint.
Think about that number for a second. 25. 25 square meters is the total footprint required to house this massive, multi-stage industrial water treatment process. To put that into perspective for you, 25 square meters is roughly the size of a standard two-car parking space, just a simple 5-meter by 5-meter square. It's honestly hard to believe that everything necessary to turn raw sewage back into clean, usable water can happen in a space where you'd normally just park your daily commuters.
So the big question we have to ask is, how does a full treatment plant actually fit here? Well, to figure that out, we're going to take a journey of the drop. We'll literally follow a single drop of wastewater from the moment it enters this facility to the moment it leaves. The secret to this spatial miracle is that the entire system is ingeniously packed into a remarkably compact prefab package, measuring just 5.0 meters long, 1.6 meters wide, and 2.0 meters high. It's like a giant puzzle, a total masterclass in spatial efficiency. Let's start the journey and see exactly how it works.
Phase 1, first line of defense. Before we can do any of the really complex chemical or biological cleaning, we have to deal with the big, nasty physical debris. This rough filtering stage is absolutely crucial to protect the sensitive machinery waiting further down the line. First, the raw wastewater splashes into the screen chamber. This is a 1.0 cubic meter tank built with thick 230 millimeter reinforced concrete walls. A tight 2 to 6 millimeter bar screen stands guard right here, catching all the big physical waste, things like rags and plastics. Once we squeeze through that screen, we immediately flow into the adjacent oil and grease trap. This is a slightly smaller 0.96 cubic meter chamber where oils and grease are just skimmed right off the top. We absolutely have to remove these oils right now, otherwise they're going to completely choke up the biological processes coming next.
Phase 2, the biological engine.
This phase is the true heart of the machine. We're transitioning from simple physical filtering to advanced biological warfare against microscopic contaminants. Because the processes here are so intense and hold so much water volume, the reinforced concrete walls are beefed up significantly, measuring a very thick 300 millimeters to safely contain all the biological heavy lifting going on inside. Our first stop in this biological engine is the equalization tank. At 4.5 cubic meters, this tank basically acts as the pacing mechanism for the entire plant. You can't just flood a system like this with uneven surges of wastewater, right? You need a steady, controlled flow. While the water waits here, it's heavily aerated. This continuous aeration ensures that absolutely nothing settles at the bottom of the tank before the real biological treatment kicks off. It keeps our water trough constantly moving and perfectly prepped.
Next up, we flow into the anoxic tank. Now, what's really interesting about this step is the sharp contrast. We literally just came from a highly aerated tank, but this 2.0 cubic meter denitrification zone is completely devoid of oxygen. It is a highly technical, totally anaerobic environment. The microscopic bacteria living in this specific tank are forced to survive without free oxygen, and to do so, they strip out harmful nitrogen from the wastewater. It's a brilliant biological trick engineered right into the flow of the plants.
From there, our water drop is pushed into the undisputed titan of the facility, the MBR tank, or membrane bioreactor. At 7.5 cubic meters, this is by far the largest tank in the entire plant. Here, a powerful 1.5 to 2.5 kilowatt blower vigorously pumps air through perforated pipes. This massive influx of oxygen fuels a hungry biofilm that literally eats the remaining organic waste. At the exact same time, the water is forced through ultrafine PVDF membranes, which act like a microscopic sieve. It's an incredibly intense, highly active purification zone.
Phase 3, final polish and disinfection.
So our water is mostly clean now, but it still needs a rigorous finish to ensure it's completely safe. The first step of this final polish happens in the chlorine contact tank. This is a 1.2 cubic meter volume tank, and we're stepping back down to 230 millimeter thick walls here. This is essentially the sterilization zone. Our water drop gets heavily zapped with precisely dosed chlorine or ozone. This chemical reaction meticulously neutralizes any lingering microscopic biological threats. It's a quick, harsh, but utterly necessary disinfection step before the final filtration.
For the grand finale, the water passes through two specialized filters. Both of these are housed in 450mm diameter vessels made of high-grade stainless steel, specifically SS304. First, the multigrade filter catches any absolute last remaining suspended solids, and then the activated carbon filter does its magic. I kind of like to think of this one as the deodorant of the plant. Its sole job is to remove any lingering colors or odors, ensuring the water that exits is crystal clear and smells like absolutely nothing at all.
Phase 4, the leftovers, also known as sludge handling. Let's move over for a second and see how this builds up. Because while the clean water has successfully exited the plant, we still have to deal with what it left behind. You can't just vaporize the physical waste that the bacteria ate and filtered out, right? It has to go somewhere. Well, this compact system has an incredibly neat way of finalizing that process. The organic waste flows into a sludge holding tank. This tank has a volume of 1.5 cubic meters and utilizes those sturdy 230mm walls. Here, the sludge is allowed to thicken up. Then it moves to step 2, the sludge drying bed. This is a 0.5 meter deep gravel bed, also holding 1.5 cubic meters. As the moisture slowly drains away through the gravel, that thick, wet organic waste transforms into a dry, highly usable manure cake, so even the waste is effectively processed into something totally manageable and useful.
Built to last, the specs.
Packing so much water, harsh chemicals, and intense biological activity into such a small footprint requires some incredibly robust civil engineering. You simply cannot afford leaks when you're operating in tight, high-density urban spaces. Looking closely at the engineering specs really shows the true brawn of this facility. The entire foundation and walls are poured using M25 grade concrete, which means it can withstand 25 newtons per square millimeter of pressure. To ensure zero leaks, an integral waterproofing compound is mixed directly into that concrete. Actually, scratch that. It's not just waterproofed, it's practically indestructible. They've built in a 300mm freeboard above the max water level to prevent any accidental overflows, and the piping is top tier. 50 to 100mm high-density polyethylene for the raw sewage, and pure SS304 stainless steel for the clean filter sections.
Now, while the physical plant itself only takes up 25 square meters, the engineers do note a slightly larger recommended plot size. They suggest a 6 meter by 6 meter plot, which equals 36 square meters. This extra 11 square meters of buffer room isn't for the treatment process itself, but rather to leave adequate room for human maintenance. It ensures technicians can easily access the tanks through those 600 by 600mm stainless steel manhole covers we just mentioned. It's just a really smart, practical design choice for real-world application.
Which leads us perfectly to our final thought. If we can achieve full 10-stage industrial wastewater purification in a footprint of just 25 square meters, how might this reshape our future cities? Imagine a world where every large apartment building, every commercial complex, or even every small neighborhood block has its own virtually invisible, self-contained water treatment facility. This tiny but mighty 25 square meter footprint doesn't just clean water, it fundamentally challenges how we think about sustainable urban design and decentralized infrastructure. It's incredibly exciting to think about what this means for our future. Thanks so much for exploring this amazing piece of engineering with me today, and keep questioning how the small things can make a massive impact.